Hello everyone, I'm Doria. Welcome to today's openEuler mini course. In this episode, we'll talk about the openRSO solution for co-deployed services. The co-deployed services sometimes share resources, such as memory. In different services using memory at the same time, access delay interference may occur. To address this problem, we introduce the openRSO solution, which performs resource scheduling and orchestration. With openRSO, shared resources in the system are scheduled and orchestrated in a unified manner for co-deployed services. Before discussing openRSO, we first need to understand co-deployment. Co-deployment essentially is mixing different services together. For example, we know the service resource utilization of data centers is low, only 10% to 20%. This wastes a large number of resources and increases O&M costs. Co-deployment emerges as a solution. By co-deploying online and offline tasks, idle online cluster resources can be used to perform offline tasks, such as batch processing. In this way, co-deployment can effectively improve data center resource utilization. Co-deployment has many service profiles, which describe the features and behavior of services. In this episode, the feature we are looking at is memory access. To achieve faster memory access, we need to get an accurate picture of latency by dynamically identifying service profiles. We know that services change while running. For example, a feature is negative at the beginning and becomes positive after a period of time. So we need a tool to help us identify the rules behind this kind of changes. But first, we need to look at interference, which occurs when the system handles low-priority batch processing services and high-priority services together. Let's learn about the layout of shared resources in the system and the interference caused by co-deployment. As shown in the figure on the left, servers generally have multiple layers of cache. The higher the cache level, the larger the capacity. In other words, L2 has a larger capacity than L1, and so on. Additionally, if L2 is sensitive, there is a high probability that L3 is sensitive, and vice versa. Shared resources in a co-deployment scenario can have a number of problems. For example, if I run online service task A with high priority and then offline service task B with low priority, task B may occupy the cache. B occupying the cache line of A will result in cache misses, affecting the performance of mission-critical services. In co-deployment, mutual interference between services is divided into the following types. The first and most common type is compute-intensive. It is the most common because data volumes are often large and memory data is sometimes discrete rather than centralized. As a result, when two computing services are running at the same time, strong unstable interference may occur. This is shown in the figure. For example, here with the spec CPU test case, we can see the blue line and the orange line without any configuration, just running normally. The sawtooth shape indicates they want to occupy each other's cache, meaning performance is heavily impacted. Sometimes we deploy latency-sensitive services. When doing so, to make services run more evenly, we must perform stability enhancement. Here, the blue line isolates the interference to a cache. The interference here is stable. The last type of interference is burst mode interference, such as k-means. As shown in the figure, cache occupancy occurs at intervals. When the garbage collection GC thread bursts, the cache is occupied or the GC thread occupies a separate cache. The system environment reduces interference to a certain extent. Additionally, high priority and low priority do not mean use more or less cache. The figure on the left shows how to allocate cache for a mission-critical service. Cat 14 indicates 14 ways of cache are used, and Cat 1 indicates one way of cache is used. If only one cache is used, performance is very poor. We can easily understand this figure, but how about the figure on the right, which shows a different situation with interference? Let's look at the normalized degradation. As shown in the figure, when the number of cache ways for the interference is 1, the degradation ratio is greater than that when the number of cache ways is 5. In the figure on the right, we only need to compare the blue line with the yellow line. For the yellow line, we added a bandwidth limit. After the bandwidth is limited, latency is significantly reduced. openRSO handles the balance of resources in each phase from 2 aspects. For example, for task A, you can view its top-down vertically. You can also view other services in the system, like task B at the same time. If task B occupies the same resource at the same time, task A will be affected. We can use algorithm to know the extent of the interference and how much performance will be affected. The structure of a server is complex. As the number of cores increases, cross-die and cross-processor structures emerge. Using the ARM64 platform as an example, the data accessed by a CPU may be stored in a cluster and also in the next cluster. In addition, data may be accessed through memory. The memory may have data on other dies, which may cause competition. When data is accessed from other dies, cross-processor access may occur. If CPUs on different dies use the same physical resource and the store operation is performed on the cluster, the original data may be flushed. This is a complex structure. The openRSO solution builds on the traditional topology. In openRSO, one CPU corresponds to one L2 or L1 cache, and one cluster corresponds to one L3 cache. In this way, we can know to which physical component die data may belong. openRSO schedules resources by organizing classes. Each class, which contains one or more threads, is a minimum entity for scheduling resource configuration and monitoring and determines cache and bandwidth usage. The advantage of this design is that a thread can be monitored as an independent entity. This is a flexible structure. This is a brief introduction to the openRSO solution. If you want to know more, please visit our SIG on Git. We hope you find it enlightening. Remember to follow us on our socials. We'll see you again in the next openEuler mini course. Thank you for watching.